So let's start with slides. We have a minute taker and Jabber relay. It's Jonathan Hoyland. Many thanks, Jonathan. If you want to say something in Jabber, please use these commands. The minute and blue sheets will be available by this link in CodeMD. It's instead of Etherpad platform. Please add your name one more time. And this is a link to the web. This is not well. I think nothing new for everyone. Just look at it if you haven't read them. This privacy and code of conduct, and the links to the RFCs. And a link to the RFC about IETF primer. So our agenda and slides are published in the data tracker. The agenda is there. So let's start with the document status. So we haven't obtained any new RFCs since our virtual meeting in April. We don't have any new RFCs in the RFC editor queue. But we have a good update on randomness improvements document. Now it's in ISG review. The author believes that all IRSG comments have been addressed, and so now it's in conflict review, in ISG review, etc. So we hope that it might be ready before Bangkok or virtual in November. We have an update of Argon 2, so the authors addressed all the concerns that were expressed. Now we're waiting for our reviewers to confirm that all their concerns have been addressed, and then the IRSG review will continue. About active CFRG drafts. First of all, SPAKE 2. We'll have a presentation from Watson just after this presentation. We have new shepherd of the document, it's me. And I think that we'll proceed with this document. We have a lot of good reviews of it because it was involved in the pack selection process. So a lot of comments, a lot of pros and cons of solutions have been expressed. So I think that it's in a good shape. And after a few updates, in my opinion, the document should be ready for further steps. We have updated version of hashtag curve document, and it's in a very good condition. And in my opinion, we'll be able to proceed with this really soon. We have VRF updated, and we have Kangaroo 12, which is unchanged, but the research group last call ended, and we asked for another literary panel review because there were not too many opinions about the document, so we'll ask for one more review. We have VOPRF updated, and today there will be a presentation about VOPRF, so all news about this. We have a research group last call on HPKE. It started in May, so please express your opinion if you want to. We don't have any changes with BLS signature. We have a lot of changes about parent-friendly curves, and we started a research group last call about 1 month ago, but we have received new opinions, especially from René, and I believe that the authors would like to address these concerns. So the ristretto is now a work item of CFRG. It has been updated, so the work is going on. About related work, we have some hopes that we'll have some news about post-quantum document because Nick Sullivan started to be involved in the process, so maybe we'll have some news about this before the next meeting. We still have some discussions about draft of John Madsen's about deterministic signatures. So the process is going on. We have a new related item for AAD limits. Chris Wood will have 10 minutes to discuss this document today. And we have two documents that are about PEG protocols that were selected during PEG selection process. So it is OPEG and the draft by Hugh Kravchik with Chris Wood and with the help of Julia Hesse is available. It has been recently updated, and in the near future it will be adopted as CFRG item after the updated version with draft IETF CFRG name will be obtained. The same thing is with draft about CPACE. We have Bjorn Haas, Julia Hesse, and today Michel Abdallah joined the team. He has a lot of very important comments about security, and we believe that his involvement will also help to make this draft as good as possible. And we have some expired drafts, but if to say about its structure, in fact, it needs to be updated, and we think that it's ready for research group last call. So that's about document status and about crypto review panel. So everybody knows the history, that it was formed in 2016. We have a wiki page, and now we have a lot of documents going through this panel. A lot of good reviews done, and extremely good reviews were done during PEG selection process. Many thanks again for all reviewers. And also currently we try to ask for reviews from crypto panel for every document that is ready, or we think that it's ready for research group last call. And our current members is on the slide. So thanks to everyone in the crypto review panel for their involvement. The reviews are really good, and we think that it's really helpful for CFRG to have good opinions. So any other business? Please say your name and say something. You know, if you want to bash an agenda or say any other stuff. If not, then we have a presentation from Watson Lab. Please, Watson, begin and tell me next slide each time you want to share slides.
Thank you, Stanislav. So today I'll be discussing Spake 2. So next slide, please. This is there'll be a bunch of next slides. So this is the draft, and it defines a PAKE with no hash to curve requirements. You can use hash to curve if you want, but it's a pre-existing work item from before the PAKE bake-off. If you look on the data tracker, you'll see a long history, and it's supporting work in the Kitten working group, and there's also deployments, Magic Wormhole, other ones I can't remember off the top of my head. So there's a recent revision, and the only thing that changed in that revision was, since we have the PAKE selection process concluded, was to clarify that this was not selected. So way forward, so we've recently regained a shepherd. I know I misspelled that. And I think it's time for a working group last call. There was significant review as part of the PAKE competition, but these are mostly high-level issues about the protocol and what it does. There weren't any, to the best of my recollection, little nits like there's a typo here, typo there. If you sent one of those emails, then it's entirely possible that it's not reflected in the revision just because of the, got lost in the shuffle. So next, please. So I can't claim, if you sent me an email about a typo, it's entirely possible it's not there. So that concludes what I have to say, unless there's any questions from the audience.
So, Watson, if you don't mind, one question from myself. As we discussed before the start of the meeting, as far as I understand, you will double check that all the concerns that were expressed during the selection process and that are reflected in the web page on the GitHub of selection process, that you will double check that it's addressed, and after that you will send us a note that the research group can read the draft, knowing that all previous comments have been addressed or at least answered. Right?
Yeah, I mean, so my recollection, which I've refreshed, is that the review process in the PAKE bake-off really, just sort of just said, okay, the protocol has the properties it has. I don't think there were specific concerns with the document, but I will double check those reviews carefully. And that's part of an artifact of the process, where it was very much a bake-off and it wasn't a document review aimed at finding issues with the documents per se.
Yes, you're right. Thank you. I believe that most of the concerns were about the protocol itself. You're right. But I think that some of them can be related to the document, so please check. Why not?
Yeah, I will. And it would be helpful if people had concerns that might not have been phrased that way, just resend them to the list.
Of course. Any other questions, concerns, comments?
This is May. I have a quick question, and that is, why did you put, there's different types of curves involved in the suites that you picked, right? The NIST curves, I think it was at 25519. They all have different representations. Why wouldn't we just pick one single curve type?
As in so if I understand your question correctly, it's why don't you limit the draft to say only use curves in short Weierstrass form or only use curves in Edwards form? And the answer is that this is based on application demand, where you have users that would like that only use the NIST curves, that have libraries that handle the NIST curves in the usual format, and they would like to expose it on the wire, or they'd like to expose Edwards points on the wire. And so that's why we did that.
Yeah, but you mentioned as an application, you mentioned what was called wormhole, which I know has been a project in the EU for about 3 years. You didn't mention any other applications, right? So it seems that this is a CFRG document. Maybe you can just do only a systematic representation of Weierstrass, and then under the hood, people can always do the calculations on the corresponding Edwards curve, right?
So, sorry, you're saying we should remove so the document is there's nothing specific about the protocol to the encoding of curve. And if the issue is the test vectors, well, they're test vectors. They're sitting in the draft. They're not. But there are applications. I mentioned the Kitten working group. So there's Kerberos applications, and that is where those vectors came from. The Magic Wormhole is not the only application.
Okay, I mean, I'm just a little bit confused because now we get lots more representation types than we ideally would need. We would now have to maintain also the Edwards stuff, and that basically the problem I see long term is that IETF we get basically a bunch of islands with different representations, all propagated into different areas. Why not just use one systematic way of doing things? It seems to be far easier to maintain, right?
Well, what we've learned from experience is that, and this is not a new issue. This came up in the discussions of Ed 25519 adoption. This came up in discussions of Curve 25519 discussion, what came up is that really the burden to use a different representation is not very much. And your core arithmetic is not affected by this. You can take any elliptic curve and put it in Weierstrass form through a very simple transformation, no matter what representation it is. And so it's much less of a burden in practice.
Yeah, so I do appreciate that. If basically the core functionality is not impacted because you have an easy mapping, why not then do the easy mapping under the, like it seems to be more or less marketing whitewashing to call everything to consider Edwards curves to be completely different than any other Weierstrass curve, right?
Okay, so also we have a comment from Björn Hasse that it might be worth adding the pointer to the recent paper with UC analysis for SPAKE 2. So the uniform composability models analysis to be presented as Björn says. Maybe Björn will comment it himself.
So, wait a moment. Do you hear me?
Yes, yes.
Okay, there's a recent paper by, I don't know all the authors, I think it's also by Michel Abdallah and Manuel, who have added a very long paper on the security analysis of SPAKE 2, and might be worth to add the link in the reference list. And regarding the question on how to handle different curves, I do see advantages for using different representations or specific optimizations for some applications. So I think it's worth considering to have Weierstrass curves in addition to other point representation, and that might strongly depend on the application type that you're having, and depending on how you implement it. If you enforce some representation, you might have as a result an increased risk of implementation pitfalls on the other side. So I think to fix one representation in the draft might be not serving all of the applications perfectly. And this is a question I'm just have asked also to Stanislav, which we will have to discuss also for CFRG and maybe opaque. For instance, for the question whether we want to add test vectors for Ristretto into drafts such as SPAKE 2 or CFRG and or opaque at some point. Or whether we don't want to, or whether we want to stick simply to short Weierstrass representations. And I'd be in the opinion to better add these options because these might prevent other pitfalls, implementation pitfalls in some applications. So, but there's no right or wrong on this topic, I think. So that's what I'd have to add.
Okay, thanks, Björn. Any comments from Watson?
I don't have anything to add.
Okay, thanks. Any more questions to Watson?
Just one more comment. This is Ben Kaduk, who I guess on paper is editor for the draft, but I haven't really been doing much, so maybe you should take me off. But I can speak a little bit to the Kerberos use case, and I think I see Greg Hudson is on the call as well. But for Kerberos, we actually have the implementation of the Edwards 25519 curve that we can, it's license compatible with our code, and we can just include it into our project. And so that's sort of the built-in functionality. We also have people who want to use the NIST curves for whatever compliance or other reasons, but we end up needing to use OpenSSL to implement those, and that has to be like a separate module that you can disable. And so there's sort of different reasons for wanting to have the different curves that happen to have the different representations. So from a practical point of view, I think we might be stuck, at least in our implementation, to have to support the different curves with the different representations.
Thanks for the comment. If we don't have any more comments, then many thanks to Watson. And before we go to the presentation from Chris Wood, we have a minor agenda bash. Jonathan Holland said in the chat that Chris Brzuska wants 5 minutes and then to ask for reviews from the CFRG for his NPRF design. So after all talks, we'll have, I think, enough time to hear Chris. And now we have Chris Wood and his presentation about AAD limits. So this is a new work item. So it's not a work item from CFRG. We added this as a related item. And so please, Chris, start.
Thanks. So, can everyone hear me okay?
Yes, yes.
Great, okay. Yeah, so this is a document that was born out of work with Felix Gunther, Martin Thompson, and Kenny Patterson, and many others in the Quick working group and the TLS working groups, as we were trying to figure out how limits on AAD algorithms apply to Quick, drawing on experiences that we got from TLS and from recent research that came out in the past year. So next slide, please. So I guess some brief background, as you all probably know, the cryptographic algorithms and the primitives that we use all have limits to them. You can't, for example, take an AED algorithm, a single key, and just encrypt data indefinitely. Doing so like effectively, or may allow an adversary to learn information about the particular algorithm in use. Or let me take a step back and say, algorithms basically have limits. And two of the limits that are, I guess, immediately or critically important for these are those that pertain to confidentiality, the secrecy of the data you're trying to encrypt, protect, and the authenticity of the data, or the integrity of the data you're trying to authenticate. The confidentiality limit of a particular AED algorithm effectively corresponds to how much data you can encrypt before you give an adversary some non-negligible advantage in distinguishing the AED from a random permutation. So in the normal, in the normal CPA game, where an adversary is interacting with either a random permutation or a particular instance of an AED algorithm key with a randomly generated key, given enough queries to this particular encryption oracle, effectively, the adversary could determine whether or not it's interacting with one of these primitives or the other. And the goal is to make it so that the adversary can't do that by limiting how much data can actually be encrypted. On the integrity side, we're more or less concerned with trying to limit how many decryption attempts can be made before an adversary can successfully forge an AED ciphertext. And similar game, AED algorithm, or an adversary is given access to a decryption oracle. You can query, and eventually, if given enough attempts, it can produce a valid AED ciphertext that decrypts successfully, and then as such forges the packet, or forges a ciphertext. So one of the, I guess, important things to note is that these limits influence the protocols which make use of these AED algorithms. So for example, TLS 1.3 has limits on how much data can be encrypted for a given connection, and the limits pertain to or specific to each of these cipher suites that are supported by the protocol. So you can check out RC 446 section 5.5 for more details there. Importantly, TLS only focuses on the confidentiality limit, and that's because TLS typically runs traditionally over TCP, which ensures in-order arrival. An adversary can really only try to forge a single packet before effectively tearing down or causing a connection failure. So in practice, the integrity limit is not really important for TLS, but for Quick, if you could advance to the next slide. please. Oh shoot. But I'll get to that in a minute. But for Quick, it is a problem. Another quick thing to note: the limits that exist in TLS are they pertain to what we call single user security, which is effectively if you look at a single instance of an AAD keyed with a single key, the adversary's goal is to break either the confidentiality or the integrity guarantees of that AAD of that specific instance. There's this other related notion called multi-user security, which considers all uses or all instances of an AAD algorithm sort of executing in parallel with different independent keys, and the adversary, of course, being able to see all of these ciphertexts that are encrypted in transit and in use. But instead, or unlike in the single user security case where the adversary's goal is to sort of break either confidentiality or integrity of a single specific AAD instance, here the goal is to break confidentiality security of any one of the instances effectively chosen at random. So depending on the application and threat model you're concerned about, single user or multi-user security bounds may be important for you. And we try to cover them both in the draft. Next slide, please. Going back to why this draft even exists in the first place, as I was saying at the beginning, there's some recent research that was done specifically for Quick, which looked at the effect of Quick's transport mechanisms and how it impacts effectively the usage of AAD algorithms inside of Quick. So as I was saying earlier, TLS doesn't really consider the integrity limit to be part of a problem in practice because, again, any single forgery attempt or adversary injecting a packet into a connection that doesn't decrypt successfully will result in connection failure, and the keys are thrown away and everything's done. Quick, in contrast, allows multiple forgery attempts because the protocol is specifically designed to allow out-of-order delivery of packets. So endpoints need to be able to process or handle, effectively what are either out-of-order packets or potentially forgery attempts from an adversary. So as a result of this work that came out, we had to go back and look at all of the different cipher suites that were in use in the protocol and see whether or not whether the limits needed to be adjusted. And several things sort of came out of that reanalysis. The first of which was that ASCCM didn't really have any analysis that could be readily or easily used. So at first we were considering just abandoning ASCCM altogether inside of Quick, which would leave just GCM and Jajapali as the only AADs that were left. But they're, with working with Martin and Felix and some others, we sort of think we got that squared away, and we went and looked at the relevant results, and we extracted the confidentiality and integrity limits from that, or a simplified version of the confidentiality integrity limits of that, and baked it into the latest Quick specification. Another thing we started to reconsider was whether or not the single user threat model was actually relevant for Quick. So there's a proposed change to the Quick specification up right now, which effectively transitions from what was limits previously considered in a single user security model over to a multi-user security model. And the reason we did this is because it seems, if you think about a single connection that's potentially performing multiple key updates, each key update, which is a process by which endpoints hash forward their traffic keys and derive new encryption keys and new nonces and whatnot, effectively introduces a new independent key into sort of the scope of that connection. And that very nicely aligns with the notion of multi-user security, where you have these multiple independent AAD instances, and an adversary's goal then is to break any single one of them, not necessarily a specific one. So basically, we started to question whether or not we had the right limits in place for all of the cipher suites that we needed to consider, and whether or not those limits were taking into account the right adversarial threat model. To sort of make matters, I guess, harder for that particular work, all of the limits that were known or published for these cipher suites were scattered across different papers using different notation, which was more often than not inconsistent. Some of the results were incomplete. So, for example, we don't really have any separate confidentiality or integrity limits for Chachapoly. The only known analysis on the limits of that particular AAD combine the two together. So instead of having a confidentiality integrity limit, you have a single AAD limit. So how many packets can you encrypt and how many packets can you decrypt, for example, or really it's blocks. How many like plain text blocks can you process before the adversary gains a non-negligible advantage in a usual AAD style game? And then some of them are incomplete. So we don't have multi-user security balance for Chachapoly either. So given this, we thought, if you can advance to the next slide, please. It would be very useful if we could sort of extract all this information that's scattered around these different papers and documents into a single place that covers all of the known AAD algorithms that we are using for Quick and TLS, and presents the formulations for the limits in a very simple, easy to digest manner, specifically targeted towards protocol designers who need to bake these limits into like protocol mechanisms, like Quick, for example. And we tried to present the limits in such a way that are easily sort of enforceable in practice. So for example, that means basing the limits on the number of message blocks that are processed in the context of a given key. And for example, what sort of success probability is reasonable for a given adversary in a given use case. For Quick specifically, we just borrowed the same success probability that we used in TLS. But in the drafts, we keep it as a variable in case people want to potentially raise it or lower it, depending on how paranoid they are. Next slide, please. So the scope of the document currently includes all AADs that are used for Quick and TLS. So it doesn't have any of the, for example, CIV AAD algorithms like ASGCM CIV, but potentially could include that in the future. Does not include any unauthenticated block cipher modes like counter mode or CBC mode or anything. And the editor copy includes both single multi-user security limits. It does not. The draft that's published in the data tracker currently does not have multi-user security. And we included both specifically because we wanted to, not to encourage or recommend any particular threat model for a given application, but to make it so that application and protocol designers could choose, whichever limit more readily applied to their given circumstance. Next slide, please. Right. So from future work, we would like to sort of expand the guidance that we have in there for protocol developers. We have some text which basically describes like how to take these limits and how to sort of imply or apply and enforce them in the context of a protocol, but surely there could be more words there to make it a bit easier for people coming at this from more of a transport perspective. It would be great if at the end we could actually compute some of these limits and bounds for common parameters. I think the ASGCM CIV RFC has such bounds pre-computed already in an appendix, and the idea would be to do something similar to that. There is the link here, if you go to the slides and you download them. There is a page in which we sort of allow people to play with certain parameters to compute these bounds sort of dynamically or interactively. And the idea would just be to sort of include that information in an appendix so that people don't have to do it themselves. And that's effectively the changes that we made to the Quick document were very much doing exactly that. I mean, while we did some of the derivation work in the document just to show that our work was correct, or to encourage people that our work was correct, at the end we just derive the limits directly and don't leave it as an exercise to the reader. Next slide, please. So some questions for the group. Felix, Martin, and I felt this was, at least we wanted to codify, the knowledge that we gained in doing this analysis for Quick and TLS. So at the very least, it was useful to us, and we're wondering whether or not this is useful to the CFRG and potentially to other IETF protocols. So it'd be helpful to know whether or not people think this is something we should keep doing and pursuing. If so, it'd be great to know if there are people who are willing to review and provide feedback. I will say, obviously, we are not perfect, and we have made arithmetic mistakes along the way, and we may have made mistakes in translating results from papers. Entirely possible, so the more eyes we have on this, the better. And assuming all those are good, I'm curious to know whether or not the RG is interested in adopting and moving this forward. And that is it. I see there's some questions.
Many thanks, Chris. So I believe that the first question was from Yuri Blumenthal. Why are you excluding SIV, SIF? Yuri, would you like to comment this?
Yes, I wonder why SIV modes are excluded, especially since at least GCM SIF already comes with pre-computed bounds. So your work will be even easier.
Yeah, as I said, that's why there's an asterisk to that on the slide. They're only excluded because we didn't type the words into the keyboard yet. There's no reason they should be excluded going forward. We don't have a very compelling reason to exclude them. Obviously, if this is a particular AED that people are using in practice, we would like to cover it here because we don't want to end up in a situation where, yet again, there are more bounds or more of these. There are multiple documents you have to consult in order to identify what the bounds are. So that's the reason. We just haven't gotten to it yet.
Many thanks.
I would like to request prioritizing it. Thank you.
Yeah, sure.
Thanks, Yuri. Then, if it's possible, a comment from me with my chair's hat off. I really support this document. I believe this is really important, and I am really happy that this is the second document on the topic of the limits of usage of the block ciphers in various modes. We recently had RFC 8645 on rekeying, and now this is a draft on usage limits on AD algorithms. I believe that is really an important work, important for all IETF, and I believe that this is one of the things that CFRG must be working on, providing the guidance to the IETF how to use crypto. So in my personal opinion, it's really a very important work. So I would be happy to support it and to review it if needed. So I think it's really great work. Thank you. And then we have comments in the chat from Scott Flutter. Scott, would you like to announce your question?
Yes. Yes. Can you hear me?
Yes.
Yeah.
And specifically with the GCM cipher suite and TLS, I don't know about Quick. They deliberately include 32 bits from KDF data inside the NOS actually used. This was designed specifically to increase the security against multi-user attacks. Does your I'm just looking at your document now. I haven't seen it before. Do you address that sort of thing?
Yeah. So the limit. Sorry, go ahead.
Or do you try to cover other usage-specific protections which are not actually part of the underlying crypto as well?
No, yeah. So that's a good question. the usage or the AEDs that we cover are those that are specifically used inside of TLO. So yes, the limits are derived based on that particular usage of ASGCM. The limits, as you suggest, are worse for multi-user security if you just apply sort of ASGCM out of the box, which TLS 1.3 and Quick do not do.
Thank you.
Then there is a question from Dmitry Bilavsky. Dmitry?
Hello. I'm very fond of this document. I strongly support its adoption, but I also am interested in adding the multilinear Gauss model MGM to the comparison, just to understand its place in the AID world. Thank you.
So we limited it to AAD algorithms that have wide adoption. And specifically, we started with those that were included in TLS and Quick. So I'm not personally opposed to it, but I would like to hear from other people as to whether or not it makes sense to include it. I'm not aware of any like large, scale uses of that particular AAD.
Okay, good.
Strong feelings. Yep.
Thank you.
If you'd like to file, there's a GitHub repository for the draft. I'll try to include a link when I'm done. If you'd like to file an issue suggesting to include it, that would be very useful.
Got it.
Thanks. There is a question from Watson. Watson, please.
So looking at the draft, it seems that these are sort of formulas copied out of papers, which is great. But then when you check them and you check that it came out of the paper, you aren't actually checking the formula. I'm wondering if because these two theorems for Cha-Cha and AES-GCM are virtually identical. Is there some way we could more formally get the right result and just plug in the block size and that one's a PRF and the other's a PRP and get out the right result? Or is that just not going to work?
I'm not sure. Maybe, but Felix, I think, is a bit more adept at figuring out the actual bounds. So he's here. I don't know, Felix, if you want to sort of tune in or chime in and answer that.
Yeah, hi. I'm not sure I entirely understood your question, Watson. In which way you suggest to make better use of the paper balance, or is that?
My suggestion is that if you write down, so you want to check that this formula is correct. And right now, it's just look at this paper, there's some huge detailed proof for AES-GCM. There's a very similar, very detailed proof for Cha-Cha, whatever. But both of these proofs are essentially the same. And so I'm wondering if there's some way to combine you have a single combined formula, check that very carefully, and then you're just plugging in some values.
So I wouldn't know whether there's the chance to give like a combined formula for the different AAD modes. I think, Chris, correct me, but our perspective would be to give some background information on how to translate kind of from the paper results, from the paper bounds to the bounds we would give in the document, so that if you're just interested in like how to apply the bounds, you wouldn't like kind of need that reference, but kind of as like a way to track down where the different numbers come from. Along that way, as Chris already mentioned, we will need to explain in quite some, well, we'll have to take care and need to explain in some detail that the different published papers do make quite varied assumptions. So we're trying to unify them, but this process of unifying introduces kind of assumptions in the translation. And I guess we'll hope to spell those out as explicitly as possible. But I guess that's still like further work on the document.
Yeah, I think that's right.
Thanks. There's also a comment from Philip Hallenbaker. Philip, would you like to say it? So there is a message from Philip in the chat that Philip supports this work and some concerns about encryption of large files. Philip, would you like to say it yourself? Philip, you're muted. We don't hear you. Okay, Philip, I'm sorry, but we can't hear you.
And Stanislav, you skipped my comment.
Sorry, please say it.
Yeah, he was just quoting SIV and then asking about post-quantum threat model. Do you want to ask a question, Johan?
Yeah, so I obviously support the document and +1 to Yuri on SIV. And I'm not even sure if it's a good question, but I'm very interested in analysis of these modes as they apply to a post-quantum threat model, obviously confidentiality and not integrity. So if that would be applicable, I would very much support it in the document.
We haven't at all used the word post-quantum in discussing this document yet. So we haven't really thought very much about it. Yeah.
Okay.
Okay, then we have a question from Dan Hawkins. Dan?
Yeah, thanks. I'm sorry, I haven't read your draft yet. I just pulled it up and I'm scanning through it. Do you talk to any of the situations where, let's say, the AAD was significantly greater than the amount of plain text, and what are there any limits that on AAD that can affect the confidentiality and integrity bounds?
Yeah. So we assume, and this is probably something we need to make very clear in the document, that the AAD is much less than any of the plain text that's being encrypted. So if you think of Quick and TLS, for example, it's just like the record headers or the packet headers. That said, there are certain cipher suites, particularly like AES-CCM, to which if there were a large amount of AAD, that would affect the limits, and the simplifications that we've made would be not accurate in those cases. So I don't know how we could. We have not discussed how to potentially deal with that assumption that we made, that the AAD is much smaller than the plain text and typically a fixed size. But it's a very good point to raise, and I'll file an issue to track it so we can have that discussion. But for right now, I don't really know of a good way to present it. Yeah.
Okay, thanks.
Yeah.
Thanks. We've got one more comment from Yuri. Yuri, would you like to tell it? Yuri?
Well, seems obvious enough. Yes, I also support this work, and I would like to upvote the suggestion to bring post-quantum in.
Okay. Thanks for the comment. So if we don't have any more comments, my proposal as a chair will be to announce a call for adoption in the mailing list. I believe that a lot of people will support this, but maybe some new comments will occur. So if no one objects, we'll have an adoption call in the CFRG mailing list. Okay, it seems that we don't have a new comment. So the last presentation is about VOPRF. Alex, please.
Hi, can you hear me okay?
Yes.
Hi. So yeah, I'm Alex. I'm just going to be talking about one of the CFRG's drafts that's currently moving forward, and that's on oblivious pseudorandom functions. And so this talk is going to be focusing on the latest updates that we've had in the 04 edition, and then we're going to hopefully canvass opinion on the state of the draft and what the next steps will be. So next slide, please. Next slide, please. So just as a recap, in case you're not familiar with the functionality, so an oblivious pseudorandom function has a client and a server, and the client's trying to learn the evaluation of a pseudorandom function on the server's key on their chosen input X. And the security behind an oblivious pseudorandom function is that this input X is blinded and is not revealed to the server during the protocol. So generally what happens is the client sends a blinded form of the input X in such a way that the server can still evaluate the pseudorandom function even with the input blinded, and then sends this blinded evaluation back, and then the client can output the PRF evaluation by unblinding its input. And obviously there's another security assumption which we're making here, which is that the server, that the client does not learn anything about the server's key. So next slide, please. And then there's a second mode of the oblivious pseudorandom function whereby everything's the same except the server sends back a zero-knowledge proof that it's used the key K in evaluating a pseudorandom function. So here the client has an extra step where they verify the proof and then unblind. And this just proves to the client that the server has actually evaluated the pseudorandom function. This is typically useful because pseudorandom function evaluations are by their very nature look random. So typically the client wouldn't be able to tell if the server just sent back some garbled bytes. So this proof attests to the fact that the server has actually evaluated the function. So next slide, please. So in this draft, we specifically talk about constructing oblivious pseudorandom functions in prime order groups. And this slide provides like a little bit of an overview of how this works. So again, the client and server have their inputs. So the client's input X, the server's K. In this setting, X is like some string of bytes, and the server's key K is a scalar in the Galois field associated with some prime order group. And there's also this public key, which is KG. So G is the generator of the group. And this is an optional extra if you want verifiability, which I'll talk about in a moment. So the first step is the client computes this hash to group, which is this H2G function of X. So this converts X, which is a string of bytes, into a group element, and then multiplies it by some random scalar R, which is known as the blind. So this computes a group element P, which it sends to the server. And for the server to evaluate the blinded pseudorandom function, it multiplies this group element P by the key K. And this gives us Q, which it sends back to the client. And in the verifiable mode, so in this VOPRF mode, the server will also provide a proof that the discrete log of the public key, which is K, is equivalent to the discrete log of Q, which is also K. And the client on receiving Q and this optional proof P, it can it's not too important here how this POF evaluation is computed, but it's based on a paper of Yaraki, Kravchuk, and Kiayish from 2014, and essentially this H computes like a random oracle evaluation over X, and then this unblinding of Q, which is like you take the inverse of R and you multiply it by Q, and this unblinds it because you remove the R. And the verifying the proof is a simple, like non-interactive zero-knowledge verification of a proof. So this is how the VOPRF works in the primary group setting. So next slide, please. So the reason these things are important is that there's a number of applications which have come out quite recently. So firstly, there's this privacy pass protocol, which has recently been made into a working group with the IETF, which uses VOPRFs extensively in constructing anonymity-preserving authorization protocols on the internet. There's the opaque draft, which constructs a password authenticated key exchange based on oblivious pseudorandom functions. And there's also a practical instantiation of privacy path related API in the Chrome browser known as the Trust Token API, and this uses functionality related to these oblivious pseudorandom functions as well. So next slide, please. And next slide. So in this version 4 of the draft, there's some major API changes which were made. So firstly, the client and server now control these global contexts, which essentially dictate whether they are operating in the oblivious pseudorandom function mode or in the verifiable oblivious pseudorandom function mode. And this just makes the function instantiations easier to write. So we can now coalesce around these 6 functions, and 2 of these are new. So the server now has a keygen function, which was required for the opaque application. And there's also a verify finalize operation. So essentially, these functions correspond to what the client and server does in the protocol. So firstly, the client runs blind, sends the output to the server, and the server returns the output, evaluates the client who unblinds, and then finalizes to return the PRF value. And this verify finalize is an optional function that's not used by the protocol, but is used by some applications for verifying that the client has performed the finalize step appropriately. There was a previous efficiency improvement known as batching, whereby the client could supply multiple inputs to the server and receive multiple evaluations with a single proof object, which attested to the fact that the server evaluated all these tokens correctly. And we've essentially removed this as default functionality because it was complicating matters. And so we now present this batching optimization as an efficiency improvement, which you can make optionally. So next slide, please. In terms of cipher suites, we previously didn't use cipher suites associated with 128-bit security groups. And this was because essentially there's this way of converting an oblivious pseudorandom function into an oracle for creating static Q-strong Diffie-Hellman samples, which can lower the security of the group. But we've reinstated these. We've reinstated cipher suites associated with these groups because there are settings such as an opaque where this oracle can't be constructed, and so you don't lower the security of those groups. So we've presented these cipher suites back into the document with the caveat that we've still got the security analysis associated with the Q-strong Diffie-Hellman attacks, and you should bear this in mind when you're implementing these cipher suites. And we used to have a host of hash functions which did various different things, but now we've removed all of these, and they also used to be HMAP and HKDF, and now we've turned this all into a single SHA-512 hash function. Next slide, please. So in terms of what cipher suites we now actually support, so we have cipher suites based around so curve 25519 and curve 448, and then we have all missed curves. And we provide advice based on each different curve on how to instantiate a prime order group from any of these curves. And that's also a new feature of this draft. And essentially, yeah, the only other thing is this hash function. So currently, as I said, we use curve 25519 and curve 448 directly. But hopefully in a future version of the draft, we're looking to replace these with either a Stretto or decaf because they give a much better interface for implementing a prime order group. So I think I'll speak about this later, but I think hopefully that's going to be something that we do in the future. So next slide, please. And so yeah, in terms of the prime order group API, we've added now like a concrete API for what we expect from a prime order group. We used to expose group elements in the inputs and outputs of the function, and we've removed that. And group elements are now only referred to internally in each of the API functions. So now they just take bytes as inputs and return bytes as outputs. And as I said, we've included instructions for implementing prime order groups for all the ECC cipher suites. I think in the NIST case, there's not too many considerations, but given the cofactor cofactors that you have with curve 25519 and 448, there's specific things that you have to watch out for. So next slide, please. So there's some other small updates. So there's now a SAGE implementation, which is as a proof of concept of the entire functionality. There was a lot of like DST usage, which wasn't, so domain separation tag usage, which wasn't consistent. So we've improved that based on what was based on the standard set in hash to curve draft. And this also allows us to remove like more complicated random oracle functionality, and we can replace it with just SHA-512 with like a prefix in a prefix-free setting. And we've also like pulled in the latest updates from hash to curve for instantiating the prime order group. So next slide, please. And yeah, so in terms of to-dos, there are some proof of concept implementations which are separate, and they're written in Go, Rust, and boring SSL. So we want to update them to be compliant with the new draft. It'd be good to get some more opinions on implementing Ristretto and decaf cyberspace. So I think Ristretto, obviously, there's an existing draft, but with decaf, I think Mike Hamburg posted sort of a candidate document to the mailing list, and it'd be good to hear whether that may be turned into either a future document or incorporated with Ristretto in the future, because that's something we'd be interested in implementing. And also we need to put in some like stable test vectors into the draft as well. Next slide, please. And so, yeah, finally, so I think some core questions that would be helpful for us to answer is we think the API should be stable now, and if anyone here has any thoughts on the state of the document on where it could be improved, on anything that we might have missed, then that'd be useful. And also if there's any sort of what people would like to see in terms of getting this document to like a research group article in the near future. So thank you.
Many thanks, Alex. So we have two questions in the chat. First of all, the question from Yuri. Yuri, would you like to say it?
It would appear that SHA-3 would serve you better in both KDF role and MAC role. So would you consider using that instead of, say, SHA-512?
So I think we'd be happy to consider it. I think so we don't explicitly do any key derivation with SHA-512. It's mainly we use it to generate random field elements. And so, I mean, if you have any opinion, if you think that SHA-3 might serve us better in that case, and that's something we're willing to consider. What sort of characteristics?
SHA-2 where PRFs sort by happening, because you cannot really have a good cryptographic hash unless it does some decentralizing. SHA-3 has being a PRF as a design requirement, explicit. And it was included in its analysis, unlike SHA-1 and SHA-2. Mm-hmm. In my opinion, that would be a good reason to consider rolling it in now, especially at the state where your draft seems to be able to accommodate it. That there is no background backwards compatibility yet that would slow you down and prevent from changing.
Okay, thank you. We will consider it.
Many thanks. Then there's a question from Bjorn Hase. Bjorn, would you like to say it or just leave it in the chat?
So I need to switch on the microphone. So in your draft, you mandatorily require the random oracle version of the map for generating the point. And this implies that you force the implementer to use the AdWords form because you need to add 2 arbitrary points. Is this actually mandatory, or would not be a simple mapping be sufficient? Because in this case, you would be free to use, for instance, the X25519 ladder implementation.
So we need a uniform group element as the output of the function. So I believe the random oracle version of that function gives us that. I'm not sure whether a simpler functionality would give us the assurances of that uniformity of the output group element.
Bjorn, any other comments? Okay, thanks. And there is a question from René Streik. René, would you like to say it?
Okay, just a quick question. I put it in the chat. I don't really understand what the benefit is of using Ristretto or some of those other functionalities in this particular application. So I would like to understand it better. Right?
So for me, at least, the benefit of using Ristretto or decaf is that they provide a unified encoding for essentially mapping these curves to prime order groups, which is the situation we need to use for the protocol. So given that Ristretto is like a current CFRG research group item, I think we would benefit from using that unified encoding rather than going down a potentially like divergent route for instantiating the prime order group.
I can add a quick comment here too. In supporting curve 25519 and curve 448 in the current draft for VOPRF, there's an expensive check that involves making sure that a potentially maliciously controlled point is not on the prime order subgroup. Using Ristretto or decaf eliminates the cost of that check.
The problem is that we then introduce essentially yet more other varieties of the 2551 family, right?
Can I real quick?
If I understand, there was a comment from Björn Haas, another question from Björn Haas about SHA-2. Björn, would you like to clarify something or leave it as this?
Not just a question, but just an observation that many implementations which use curve 25519 also have come with an implementation of SHA-512 because of the use in add25519 signatures. So that's a good reason, in my opinion, to pair these 2 algorithms together. And this is not so common with SHA-3. So one might have more difficulty in finding the implementations existing code.
Okay, thanks for this comment. Any other comments, questions?
I'd just like to second that. This is Chris. I mean, SHA-3 is great. It's not really widespread enough that it would make the implementation story for protocols dependent on OPRF more difficult. Like opaque, for example, requires the OPRF. And if we were to integrate opaque into TLS, as we were sort of working to do, that would introduce this new SHA-3 dependency on like a TLS stack, which not all TLS stacks have right now. So I think sticking with SHA-512 makes sense.
Okay, any other comments, concerns, questions? Okay, so then thanks, Alex. And so we have the last item. It was from the Oh, sorry. A comment from Yuri. Yuri, would you like to disagree about SHA-3? Yuri?
Just to emphasize the point that it is relatively new, but unlike previous SHA versions, this one is a result of an international competition. It comes with formal proofs and much better explicit design requirements. And since the protocols and functions we are talking about are also new, I do not see a concern with pairing something that hasn't been used much before with something that hasn't been used much before. The argument that TLS, for example, does not normally, currently, uses SHA-3. Surprise, it doesn't use opaque, it doesn't use verifiable PRF, it doesn't use a lot of other things. So what? You add code for this, you could add code for that.
I think if we need it later on, we can just add a new Cypress suite to introduce SHA-3. Like, for right now, I think sticking with SHA-512 is fine. I definitely agree with the points that you made, but the entire reason we have Cypress suites is to allow this extensibility into the future. So I think we should do that.
Okay, many thanks for the comments. So here's the last item, Christopher Mruzka. Christopher, please.
Thank you for including me on short notice. So I'm Chris, and so we have a cryptographically relevant change suggestion to the IETF standard for messaging layer security. And John Turner suggested to me yesterday to present the suggestion here to get your attention for cryptographic validation. So let me, can you share content? Somehow it looks like it cannot share content. Sorry.
So the share content button just on the right from the camera.
Right. This is annoying. All right.
If you have it downloaded somewhere, you can just send the link to the chat, and I'll share the content instead of you.
Okay. I will. Yeah. Let's do this one. So wanted to share a bit more, but maybe you can just open this. Okay.
Or you can try to proceed without slides, if it's possible.
Could you be so kind and visit the link that I sent in an email today? And then.
In fact, I can see the link in the chat. The last question I see is the comment from Alexei Melnikov about SHA-3 debate to the CFRG members. Yes, I see this. Okay.
Thank you.
So it's not the slides. It's a little bit of...
Please go to page 8.
Sorry.
Page 8.
Page 8. Okay.
Page 8.
So there are no numbers on the pages.
Sorry, further, one page further. Apologies for this. Okay, one page back, and then right there. Okay, good. So yeah, very good. The lower diagram is the one that I would like to talk about. So this is part of the key schedule of the current draft of the messaging layer security protocol. And at the top, you see there is an init secret that goes into the key derivation. And then from the left comes a PSK. And then a little bit later, there comes this commit secret. And what these kind of extract, expand, extract calls do is that they combine these three keys into the epoch secret, which should be pseudo-random if either of the three keys is pseudo-random. And then the last expand function derives a bunch of several keys from the epoch secret. So let me first say what is the suggestion how to change this, and then afterwards explain why it was suggested to change it. So the suggestion to change it is on the next page.
The next pages?
Yeah, the next page. Yeah, very good. Thanks. Yeah, perfect. So so the idea is to replace this very sequential construction by a parallel construction where one runs each of the three secrets through an expand function, then XORs the result, and then feeds the result into this expand function to derive the different secrets. So okay, so this is a suggestion for the change. Why was this change suggested? So the first observation is that this new function is more parallel and maybe also a little bit simpler construction. But the actual issue is that the extract function in the current draft needs to be a dual PRF. Could you go back to the previous page? So so this this extract function, the top extract function, it needs to behave as a PRF when it's keyed by the PSK, and it needs to behave as a PRF when it's keyed with the init secret. The issue is if either of the two inputs is malleable, then one might twice and therefore has a dual PRF functionality for this extract function. So the original suggestion for this extract function had this idea that for one of the directions, the key material is only used once. And so in this case, one relies on other cryptographic means ensuring that key material is only used once. So for the new construction, could you go to the next page again? What one needs to observe is that XOR is, of course, like extremely malleable operation. It's not a collision-resistant operation. What is used in these three expand calls is this context value, which needs to be a unique value and a label to have domain separation. And because this context value is the same in all the three expand calls, the resulting values always change simultaneously. So this unique value context is used once for domain separation for the pseudo-randomness. And then later in the lower expand call, you see it's also used. And here it's ensuring that you get unique outputs. So the collision resistance is provided by this last expand call and having a different context value in each of these calls to this figure primitive. So the IETF working group for MLS like this idea, but not many cryptographers have looked at it. So we would like to get some feedback, and so I'm sorry for not having kind of prepared a formal presentation of this proposal, but mainly wanted to raise your attention. There is this paper that you can read if you're interested, or you can also contact me and discuss the proof or give me any feedback. You can also give me feedback now, but mainly I wanted to raise your attention that there's a cryptographic relevant change in the MLS working group where we would like to have some feedback. That's it.
Hi, Christopher. Quick question. Can we include your paper as a slides in our slide deck for CFRG?
Yes.
Thanks. That will be just useful for people going back through this. Thanks.
Thanks. Thanks, Chris. So there are two questions. The first question is from Chelsea. Chelsea, please.
Hi. Yeah, so this is a really interesting idea. Can you talk about your proofs and how maybe your proofs of security operate within the larger MLS sort of context, and if there's any kind of gaps that you see between like where your proofs of security are and like where the larger protocol is for MLS?
Okay, all right. Kind of well, I guess I just spent 4 years working on the TLS key schedule, so the kind of the MLS proof as a kind of complete proof with all details as a computational proof, at least is not there, but this is kind of modular change, which you could also adapt in the same way for TLS. So this only changes the way a local computation is done, whereas the interface with other primitives remains the same.
Okay, so you don't see, like, just at looking at this at a high level, you don't see any gaps or assumptions that you're making between how to apply the TLS context in here?
Sorry?
Oh, just like any kind of gaps from when you apply this in a TLS context to applying it in the MLS context.
No, I think from my perspective, the most important part is getting hold of this unique context value, and from the discussion in the working group, this seemed not to be a problem. But yeah, I don't see.
Thanks. Then there is a question or comment from Watson. Watson, please.
So my question is, why not just run everything through SHA-3? I mean, it's supposed to have with appropriate differentiators on each input, it's supposed to have the right properties to do this sort of randomness extraction.
So you mean to replace the XOR with SHA-3? Or do you mean to repaint everything with SHA-3?
Yeah, what you want to do is you want to take in a bunch of inputs and you want to derive an arbitrary amount of output data that's random if the inputs are random. And this is exactly the sort of thing the sponge construction gives you.
Okay, excellent question. So the issue is that the thing that I would like to prevent is that key material is used twice when some other key material changes. Say you have a big group and something goes wrong and each party uses like some of these secrets, and so you have multiple derivations. 3 people use the same commit secret, 3 people use the same PSK, 3 people use the same init secret, each time with 2 different other values. So then you don't have any entropy left, and you need some sort of kind of multi-call security that you can rely on from your primitive. And I don't think that SHA-3 has proof for this type of properties.
Thank you. And now there is a question from Jonathan Holland to Watson. I don't know whether Jonathan wants to discuss it just in the chat or no. Instead, just in the chat.
Can you hear me?
Yes.
Okay. Yeah, I think the other key thing is that SHA-3 can't be parallelized. So if you have 100,000 inputs, then you would have to do it all A, then B, then C, rather than doing it in sets of trees and vectors. But Moskowitz says it is parallel stuff.
Yeah, I don't think this question is so within the expand function. This expand function is usually implemented using an implementation of an HMAC. HMAC uses a hash function. I don't know what's currently supposed to be that hash function, but like supposing it's SHA-3, then I think it might be used anyway. But I'm not sure which hash function is currently supposed to be used in MLS. Yeah, but anyway, this type of multi-called security is not something that I think SHA-3 has approved for. It would be an extremely exotic property to provide.
Okay, thanks. Maybe if there is some discussion about KMAC and HMAC and C-Shake, it can be moved to the mailing list. In fact, we have 3 minutes left. So thanks, Chris. We'll upload your PDF to the meeting materials. So maybe any concluding comments from anyone, any other business? Very short. 1, 2, 3. Okay, thanks. So thanks everyone. Hope that we'll have some chance to meet in person soon. Thank you very much. Have a nice meeting.